Hello, Chemistry 30. This is our third lesson in acids and bases. This is monoprotic versus polyprotic. In this lesson, we will compare monoprotic versus polyprotic acids and bases. We will then predict polyprotic Bronsted-Lowry reactions. We will move forward with the acid ionization constant, Ka, and then finally we will compare the theory and calculations involved with strong and weak acids. There will be 5 examples throughout the lesson. Monoprotic versus polyprotic. An acid/base that can only donate/accept one proton is called monoprotic. For example, the following acids HCl and HNO3 only have one hydrogen in their chemical formula. Therefore, each can only donate one hydrogen, making both acids monoprotic. The base HSO4- is monoprotic because it can only accept one hydrogen. If you look at the table of acids and bases in the Chemistry 30 data booklet, you will notice that most bases have a negative charge. This negative charge represents that they can gain a positive charge. They can gain a hydrogen ion. If a base only has a charge of -1 or just a minus, it can only gain one hydrogen, making it monoprotic. There's a few bases that don't have a negative charge. For example, H2O and NH3, both of those bases can again only gain one hydrogen. An acid/base that can donate/accept more than one hydrogen or proton is called polyprotic. For example, H2SO3 is considered diprotic because it can donate 2 protons. It has 2 hydrogens in its chemical formula. H3PO4 can donate 3 protons. It is considered triprotic. That is because it has 3 hydrogens in its chemical formula. Bases that have a negative charge greater than -1 can accept more than one hydrogen. Therefore, they can be considered polyprotic. For example, PO4 3- can accept up to 3 hydrogen ions. Once it gains a first hydrogen ion, it becomes HPO4 2-. After it gains a second, it becomes H2PO4-. And finally, when it gains a third hydrogen ion, it becomes H3PO4. There is no longer a charge on this molecule, therefore, it can no longer gain hydrogen ions. Example number 1. Label each of the following as monoprotic or polyprotic acids. Pause the video and attempt this example. For our first 3 chemical formulas, we have the following answers. And for our remaining 2, we have the following answers. If we look at our first acid, H2 HSO4. It has 2 hydrogens in its chemical formula, therefore it's polyprotic. Our next acid, HOOCCOOH, is also polyprotic because it has multiple hydrogens in its chemical formula. Our next acid is a little unusual. It is HCOOH. There are multiple hydrogens in the chemical formula, but this acid is considered monoprotic. The reason why is because hydrogens directly attached to a carbon in a covalent molecule will not be able to be removed. They will not ionize. Therefore, the only hydrogen that can be removed from this chemical formula is the hydrogen at the end, making this acid monoprotic. That is the same for our fourth chemical formula. The 3 hydrogens attached to the carbon will not ionize. The only hydrogen that will ionize in this acid is the hydrogen at the end, making it monoprotic. And our last chemical formula, H2PO4-. This chemical formula has 2 hydrogens, therefore it will be polyprotic. Example number 2. Label each of the following as monoprotic/polyprotic acids and monoprotic/polyprotic bases. Pause the video and attempt this example. For our first 3 chemical formula, we have the following answers. Our first chemical formula, HSO4-, it has 1 hydrogen, therefore it's a monoprotic acid, and it has a -1 charge, meaning it can only gain 1 hydrogen, making this a monoprotic base. Our next chemical formula, H2, it has 2 hydrogens, therefore it's a polyprotic acid, and it has a charge of -1, making it a monoprotic base. Our third chemical formula, HPO42-, has 1 hydrogen, making it a monoprotic acid, and it has a charge of 2-, making it a polyprotic base. For our last 3 chemical formulas, we have the following answers. HCO3-, this is going to be considered a monoprotic acid because this is an ion and this hydrogen can be removed. It has a charge of -1, so it's a monoprotic base. H2O is both a monoprotic acid and a monoprotic base. And then finally, SO3-2- is only a polyprotic base because it does not have a hydrogen available to donate. Polyprotic Bronsted-Lowry reactions. Reactions involving polyprotic acids and bases involve the same principles as Bronsted-Lowry reaction predictions. So we can use the same theory that we did in lesson AB2. We only transfer 1 proton at a time, and it's always going to be from the strongest acid to the strongest base. If we only transfer 1 proton at a time, we will have multiple reactions. For example, we may have 1 and 2 reactions. At the end, we are going to combine these reactions together to get a net chemical equation. Example number 3. Predict the Bronsted-Lowry reaction when potassium hydroxide is continuously added to oxalic acid until no more reactions occur. Pause the video and attempt this example. Step number 1, we have to list all of the species present that can react. To do so, we have potassium hydroxide, which is an ionic compound, so we break it apart into its ions, K plus and OH minus. Oxalic acid is a weak acid, so we keep it the same, HOO, CCOOH. And remember, H2O is always available in the solution. We have to list all of the species as either an acid or a base, and finally pick our strongest acid, which is oxalic acid, and our strongest base, which is OH minus. We can then write our first chemical equation. So we have oxalic acid transferring and giving a hydrogen to OH minus to then form the products HOO, CCOO minus plus H2O. HOO, CCOO minus still has another hydrogen that it can transfer. At this point, it's important to note that we have the following species available in solution. We have the products HOO, CCOO minus, and H2O, but we are also continuously adding potassium hydroxide. Therefore, it will always be a species available to react. So now in our second chemical equation, we're going to take our remaining strongest acid, HOO, CCOO minus, and again, we're going to react it with OH minus to form the following products. At this point in time, OOCCOO2 minus no longer has any more hydrogens to transfer, so this reaction can no longer occur. We have to determine the net chemical equation, so we have to cancel species that appear on either side of the chemical equation, known as spectators. So we've canceled out HOO, CCOO minus, and when we combine the two reactions together, we are left with the following net polyprotic Bronsted-Lowry reaction. At this point in time, we're going to move forward with the calculations component of the acid and base unit. When performing calculations, different theories can be used to write chemical equations. Over the next two slides, we will compare the theories. When performing strong acid calculations, it's typically easier to use a modified Arrhenius chemical equation. For example, when we put HCl in water, it is going to react with water, forming H3O plus and Cl minus. We can still use a Bronsted-Lowry equation, but it doesn't quite work as well. To do so, we have to list all of the species, and then again pick our strongest acid and our strongest base. When we do so, we are left with the following chemical equation. H3O plus reacts with water to form, again, H3O plus and H2O. This proceeds at a quantitative reaction, meaning the products will be greater than 99%. This reaction doesn't make sense and is not preferred because the reactants are the same as the products. So when performing strong acid calculations, it is the best to use the modified Arrhenius theory. When performing weak acid calculations, it is easier, again, to use modified Arrhenius chemical equations. For example, if we have the weak acid H, SO4 minus, it will again react with water to form an equilibrium reaction, producing H3O plus and SO4 2 minus. It is important to note that the Bronsted-Lowry reaction will also work, and it will produce the same chemical equation. If we list the species that are present, we only have HSO4- and H2O. HSO4- will be our strongest acid, therefore H2O has to be our strongest base. This provides the same chemical reaction that was shown above. So you can use either of the theories to write a chemical equation, but it is typically easier and requires less time to write a modified Arrhenius chemical equation. Acid ionization constant. Determine the acid ionization constant, Ka, for the general ionization equation of an acid below. Remember Kc? Well, Ka is very similar. Pause the video and attempt this example. The Ka expression for the following equilibrium reaction is Ka equals the concentration of the products over the concentration of the reactants. Ka is identical to Kc. The only chemical substance that isn't included in Ka is H2O. That's because it is the only liquid in the chemical equation. Therefore, it will not be included in the Ka expression. It's important to note that a larger Ka value represents a stronger acid. If Ka is a larger value, that means that the products are more favored. Therefore, the acid is ionizing to produce more H3O+ and A-. Again, a larger Ka value represents a stronger acid. Strong acids. Strong acids ionize 100% in water, and they do not form equilibriums. The 6 strong acids typically have low pH values, and they are found at the top of the data table on page 8 and 9 of the Chemistry 30 data booklet. If we look at the following general equation for an acid, if Ha is a strong acid, this reaction will proceed 100% to completion, meaning the products will be greater than 99%. This is a quantitative reaction and is not in equilibrium. Therefore, once the reaction has occurred, the concentration of H3O+, the product, should be equal to the concentration of the original acid, Ha. Stoichiometry can then be used to calculate the concentration of H3O+ or to find the pH of a strong acid solution. Example number 4. Calculate the concentration of H3O+ and the pH value of a 0.1 moles per liter solution of nitric acid. Pause the video and attempt this example. Before we perform the calculation, it's extremely important to note if the question provides a strong or weak acid, because the calculations are very different. Nitric acid is a strong acid. Therefore, we will use stoichiometry to determine the concentration of H3O+ and to find the pH value. We can first start with a modified Arrhenius chemical equation. Nitric acid is going to react with water to produce H3O+ and NO3-. Using this chemical equation, we can perform a stoichiometry calculation to find the concentration of H3O+. To find the pH value, we have to take the negative log of the concentration of H3O+. So therefore, pH is going to be equal to the negative log of 0.1 moles per liter. As a result, that calculation provides us with 1.0 as a pH value. We are starting with one significant digit in our question. Therefore, our answer has one significant digit. Remember, everything after the decimal place in a pH value is considered significant. Therefore, the 0 in our answer is the only significant digit. There is one exception to strong acids, and that is H2SO4. Sulfuric acid is the only strong acid that does not ionize 100% in water. That is because it is the only strong polyprotic acid. It is pretty rare that a question will be asked regarding sulfuric acid, but the theory is the first hydrogen atom will ionize 100%. So therefore, a stoichiometry calculation can be used. But as a result, we are left with HSO4-, and this is a weak acid. Weak acids ionize less than 50%, and they form equilibrium reactions. Therefore, stoichiometry can no longer be used. Calculations involving weak acids include ice tables. Weak acids. As stated, weak acids ionize less than 50% in water, creating reactant-favored equilibriums. For example, if HA is a weak acid, it will again react with water to form an equilibrium reaction, producing H3O+ and A-. This reaction will be reactant favored, and therefore the products will be less than 50%. Ice tables must be used to find equilibrium concentrations involving weak acids. There is a rule of 1,000 that applies for weak acids. This makes calculations much easier. If the initial concentration of the acid divided by the Ka of the acid is greater than 100%, then the plus X or the minus X can be removed from the Ka expression. This will be shown in the last example. Example number 5. Determine the equilibrium concentrations for each species in a 2.0 moles per liter acetic acid solution. Pause the video and attempt this example. To determine equilibrium concentrations, we first need a chemical equation. We have our weak acid reacting with water, forming H3O+ and CH3COO-. We have the initial concentration of the acid, which was given in the question. And since they did not state what the concentration of the products were, we are going to assume they are 0. And remember, H2O is not included because it's the only liquid in this chemical equation. We do not know an equilibrium value. Therefore, we cannot find a change value. So change is going to be an unknown variable. Change will be X. It will be minus X for the reactants and plus X for the products. As a result, at equilibrium, we have the following concentration values. Before we move forward with the Ka expression, we can check to see if the rule of 1,000 applies. And the rule of 1,000 is, again, the initial concentration of the acid divided by the Ka of the acid. That is 2.0 divided by 1.8 times 10 to the negative fifth. This Ka value for acetic acid is found in the Chemistry 30 data booklet. If this calculation is performed, the answer will be greater than 1,000. Therefore, the rule of 1,000 does apply. When we write the Ka expression, it is again the concentration of the products divided by the concentration of the reactants. Our Ka, 1.8 times 10 to the negative fifth, equals x times x divided by 2.0 minus x. Since the rule of 1,000 did apply, we can remove the minus x from the denominator. This makes the calculation much easier. As a result, when we solve for x, we are left with 0.0060. We can then sub the x value in to calculate our equilibrium concentrations. The equilibrium concentrations of both products is 0.0060 moles per liter. The concentration of our reactant CH3COOH at equilibrium is 2.0 minus 0.0060, which results in an answer of 1.994. Since we are required to round to two significant digits, our final answer will be 2.0 moles per liter. Moving forward, we will explore the concepts of Kw and Kb.